A very good afternoon to all the course participants of the outreach program on Geographical Information Science. I am Vandita Srivastava and you are watching this program. We are going to discuss today some concepts of spatial data analysis in geospatial domain. So I hope you recall my lecture of Introduction to GIS and Overview of Geospatial Technology, wherein we had discussed about various concepts and various applications, various steps that are followed. So today I will discuss more about the spatial analysis. So let us begin with the lecture. We'll be talking about following contents. Why we wish to carry out a spatial analysis. I had already given a background in my introductory lecture. We'll talk a little more detail about what is spatial analysis and what are various queries, attribute and spatial queries, and various types of analysis that are there and steps involved in a GIS analysis project. And also I'll give you a conceptual example of site suitability analysis, and then we will talk about various classification of functions. So based upon the classification that is presented here, we will talk about these four category of functions: retrieval and selection operations, measurement and classification and reclassification operations, overlay operations, and then neighborhood and connectivity operations. The more of the neighborhood and connectivity will be talked in the network analysis class, but I'll be giving you some basic overview of that. And then we'll talk about some basic common points. So that will be my agenda for these two lectures, that is today and tomorrow. So let us begin with the lecture. We'll talk about those basic concepts of spatial analysis and various types of spatial analysis and steps involved with an example. So why we carry out spatial analysis? If you recall the 4 W's and 1 H, the what, when, where, why and how. And anything that is pertaining to geography can be studied with GIS. So here are some reasons. We would like to understand and study the real world processes by applying certain manipulation criteria and integration criteria, and we will do integrated modeling. So that could be one reason. For example, the soil erosion is taking place, floods are occurring, the biodiversity is changing, the afforestation or deforestation is happening. So how much afforestation has happened, or how much deforestation has happened as an outcome of various anthropogenic activities, how much afforestation has happened as an outcome of various efforts that are put towards planting trees. So if we want to see the impact of human activities, or if we wish to see the natural processes, we want to understand the process of like I said, the soil erosion or any such processes, we can describe our study area in the geospatial domain, and then we try to develop certain manipulation criteria and try to reveal some information that was either not present or was hidden in the data set. So we can also carry out integrated modeling, as I said. So these are some of the reasons why we should carry out spatial analysis. Now what is this integrated modeling? I'll explain you here in this diagram. You take some part of geographic Earth or any planet for that matter as your study area. This part of geographic Earth is your study area. You call it as your study area, and in this study area you try to extract each layer, the thematic layer, administrative layer, topographical layer, and then you try to represent various relevant variables with the help of these thematic these layers, and then you try to create some new maps. It could be intermediary map or it could be your final map. So this new map is a function of these layers, this map and that map, and then you process it in a cyclic manner to create another new map, which again becomes part of your data set for creating another new map. So compute this map plus that map for new map, and then make it as a part of another new map. So spatial modeling involves cyclic processing, retrieving one or more maps from the database which are used to create a new map. Now this map becomes part of the data set. That is why you call it as cyclic. No, it is a cyclic process. So that is what is integration and modeling of spatial data. We will see a lot of examples of these. So what is so special about this spatial analysis? Please notice the spellings are different. This spatial is, and this is SPATIAL, pertaining to space. So what is so special? Because as I told you in my introductory lecture, that like you have these CAD and CAM packages which can deal with the talk about the spatial part of it. Then there are database management packages which deal with the attribute information, the locational information. But GIS is unique in the sense that it can link both the two types of data, and because you are able to link them, you can analyze them together. The linked data can be analyzed. That is what is special about GIS, and it is these unique capabilities of analysis that make it unique because of the linking. So you can answer all the questions that pertain to geography. I already gave you example of these questions, which are what, where, when, why and how, and you can apply them on anything that is of spatial relevance. So for example, what will be of spatial relevance? That is pertaining to space, that any such problem. For example, if fire has ignited at one place, how it is going to spread in space and time? What are most suitable locations of a dam? So you can carry out various kinds of modelings. So this, what are most suitable locations of a dam? If you wish to construct a dam on a water body, on a river, you are trying to prescribe a model for construction of dam. So it is called prescriptive modeling. You could also ask a question saying, please tell me if fire has ignited at point XY, how it is going to spread in space and in time. Such kind of analysis or modeling will be called as predictive modeling, because you are trying to predict in space and in time, right? So you can answer all these questions because they are of spatial relevance. Now how you do this? You break down your task into several steps, and then you try to ask smaller queries. So when you ask a query, because you remember we talked about the vector, this attribute information and locational information, accordingly we can ask two type of queries. What kind of information we are accessing to answer that query. So that will decide what kind of query it is. So query could be of attribute nature or of spatial nature, and then you could combine these two type of queries in order to ask some complicated questions. So I'll just give you an example like attribute query, spatial query, and generation of new data set from the original data set by asking certain queries, also applying certain criterias. So scope of spatial analysis ranges from a simple query to about some spatial phenomena to very complicated combination of attribute and spatial queries and alteration of the original data. I'll be talking about all those functionalities with you in these two lectures. So let us understand what is an attribute query. It requires processing of attribute data exclusive of spatial information. So for example, if I have a parcel map which is here represented here, and its attributes like the parcel number, size, value and land use type of each parcel, they are listed here. Now suppose I ask a question to the database, once having prepared the database of a study area. If I ask, please show me all the parcel numbers and values where land use is commercial. If I ask this kind of query, to answer this query, so first of all, what is the answer of this query? That parcel number and value where land use is commercial. So parcel number is, so this is commercial here, so 102 and 104, and value is 200,000 and 250,000. That is the answer. Now to answer this question, I have to look only at the tabular information. I don't need to look at the map. Therefore, this query is an attribute query. But if I needed to process the spatial information to answer a query, then it would be a spatial query. A real world query could be a complex combination of these two. So, so that's an attribute query. Now, similarly, if you look at this, suppose I tell my position is here, I am standing here, okay, where my cursor is. I hope you are all able to see the cursor. So, if I'm standing here, please show me all the parcels that are within 5 meter distance or 10 meter distance. If we ask this kind of query, we need to, because the query itself has got a special component in this question, to process it also requires special information. So I need this map to answer this query, and basically it will create a buffer distance of 5 meter around the point of concern, and it will show all the parcels. By chance this particular parcel is the only one that is selected because this is the only one within 5 meter distance, let's say. So so this is the answer, but to answer this we require to process the map information, and that's why it is a map query or a special query or locational query. Fine. So now, as I told, that a query in real world will be a complex combination of these two. We will actually see some examples of those. So that was about simple querying. Now I'll talk to you about the types of various analysis that are present, that are possible in geospatial domain, and these are single layer operations. You can perform various kinds of single layer operations such as buffer zone and Thesan polygons. There are many types of single layer operations that you can perform on one layer at a time. Then you can also you can combine more than one layers, that is 2 layers or more, and you can generate another new information. So such kind of multi-layer operations are possible both in raster as well as in vector. We will see some of the topological overlays as well as some of the raster operations to show you the multi-layer operations. And then geometric modeling is possible, that is, you could calculate the distances between various features, you could calculate various other parameters such as area, length and perimeter of line and polygon maps, and then geometric buffers you could calculate, and many other actually measurements you can make out, you can calculate for the given layers. Then you could also carry out spatial analysis for point features. So that is called as point pattern analysis, which basically is a set of various indices that you could calculate for the point features. Then for studying the line features, we have network analysis. Various applications are involved. I'll talk about each one of them in the detail in the later part of my lecture tomorrow. And then surface analysis, which is basically studying the third dimension with respect to x and y. So this third dimension could be anything, could be elevation, could be topography, could be crime potential, could be population, or any disease, distribution of disease or occurrence of disease. Okay, so you could also carry out fuzzy spatial analysis, which means you will incorporate the fuzziness of nature, because the nature is not Boolean. But this theory, fuzzy theory, came later after the Boolean theory, but it is more realistic to represent your features in fuzzy mode, like any natural phenomena such as where is the bank of a shallow river. So you cannot have a single line that will tell this is the bank if you have a shallow river. Now if it is a very deep river, then usually you have crisp boundaries, but when you have sandy layer and there's a gradually it is changing from land to water, then you have a gradual change. You cannot put the crisp boundary there. So any such thing which is fuzzy in nature, like the soil types, the change of soil from one type to another is not abrupt, it is gradual. So to represent this fuzziness, you can incorporate this using the fuzzy tools in spatial analysis. So that is what I refer to here as fuzzy spatial analysis. Then you can perform geostatistical analysis, which considers which is not based upon classical statistics, which we usually do in our calculations, but it is based on the theory of regionalized variables that was proposed by Georges Mathurin, a French mathematician, and also there was so I'll maybe talk about this in detail in that later part, but this is what is the basics, that it is not based upon the classical statistics, but it is based upon geostatistics, based upon the theory of regionalized variables and based upon the concept of autocorrelation of a variable with distance. So a variable is related to itself in space with its distance. So things that are farther apart are different than the things that are closer apart. The things that are closer apart will be similar. That is, in nutshell, you can understand. And then raster or grid analysis. All these things that you could perform in vector domain, you could also perform in raster, or vice versa, with some limitations here and there. But then grid analysis is more suited for continuous kind of features, which we call them as fields. So depending upon what is your purpose and what kind of accuracies you are looking for and what kind of representation you want, what is the source of your data, based upon several factors you will decide whether you want to do it, and where your data is available, the source of data. So based upon all these, you will decide whether you want to carry out this analysis partly in raster and partly vector, or in one of them. So accordingly you can choose the tools. All these tools are available in most of the GIS software. So that was a list of the types of analysis. We will discuss them in detail little later. I have given you a brief of them. And now I'll also tell you that what are the functionalities present in any GIS software for carrying out spatial analysis. They are categorized into 4 categories. The first one is a simple operations such as retrieval and measurement, selection procedures. So retrieval, selection and measurement formulates the first category of spatial functions, wherein manipulation is not required. But then there is also reclassification. Okay, in reclassification sometimes some merging may be required. In overlay operations, intersections take place, new topology is built. So overlay operations are little more, you can say, as a second step or little more advanced than these retrieval, selection, measurement operations. And then we also, these first 3 set of operations do not consider about the neighborhoods, but this last category, neighborhood and connectivity functions, they also consider the neighborhood of a feature or its surroundings. So we'll talk about these little later. First, let me show you one, first of all, the steps to perform any GIS project suppose we have taken. So what will be the various steps involved in a GIS project? So I'll be discussing with you about these steps, and then we'll see one example. So the first step is to establish an objective, and you make it more crisp by identifying the criteria for analysis. That is the step number 1. Then you select the right parameters for integration based upon the purpose of your study. So once you decide that these are the right parameters, you identify what variables you require, and you start collecting them either through primary survey or secondary survey, and then you bring them into the GIS system through the process of digitization, georeferencing. Whatever steps are required, you will perform those steps and bring the data to the GIS system, and then prepare this data for analysis. So you require to prepare both spatial data as well as attribute data for processing for further spatial analysis. Then you will perform spatial and tabular operations, carry out integrated modeling by bringing all of them together at one platform. Please note that they have to be there should be some overlap when you perform the overlay operations. When you do this integrated modeling, there has to be some overlap, and the data should be georeferenced together. So these are the 2 requirements. And then once you carry out this analysis, if you are satisfied, you first evaluate the result. If you are satisfied, you can go ahead with producing the output. Otherwise, you refine your analysis by manipulating the criteria or by changing some. Wherever you are not satisfied, you will go back up to that step, and then you will redo the exercise based upon those suggestions that you got in the interpretation and evaluation process in step number 7. And if you are satisfied, then you will produce the outcome. So refine your analysis if necessary. Fine. So these are the steps involved in carrying out any GIS analysis project. Now I'll give you an example of these steps in my short example. So let us say the first step is to establish the objective, and then you make this objective more crisp by giving criteria for analysis. So let us say that your objective is to log trees from forest. Okay, that is your basic objective. You are a timber company and you wish to log trees from forest. Now you all know that logging from forest could be very serious if the environment is not taken care of. It could harm our environment. So if I am a techno manager who wants to log trees from forest, I also want to, let's say as a timber company, I wish to earn profit, but then I don't want to harm the environment. So so that there is no question on my this logging exercise or logging task, and also I protect the environment. If that is my objective, then what kind of criteria I could set? So I will say that because I want to earn profit, I will say that I want to log specific trees, specific species of the trees from forest. So let us say I wish to log only ponderosa pine to be earning profits. So to be profitable, I wish to log ponderosa pine. Now that is my first criteria, because that is the whole idea of my logging exercise, right? Now I know that the moment I start logging, the environment will get affected. So I say my slope, I need to consider the slope, because if I log from the steepy slopes, the soil erosion will take place. The good quality soil will go into water. It will reduce the water holding capacity of a particular water body, and it will also lose, we will lose that much that refined soil. So we don't want that to happen. We want to protect our water quality as well as our land. So we can say we will not log from steepy slopes. We can make this criteria more specific by saying that to avoid soil erosion process, we will not log more than 20 degrees. This now 20 degrees can be changed depending upon what study area we are in, or maybe we can take experts' advice, but roughly we will not log steepy slopes. That is what it means. So that is we have listed as our criteria. We can also say that the water quality will get affected if we log. So we will say we will not log any area that is falling within 400 meters. Now again, this 400 meters can be changed depending upon the expert's advice or our knowledge. So we will say to maintain water quality, the areas within 400 meters of the wetlands present in the study area would not be logged. Fine. And we also know that if we log trees, if there is some species residing and it is already declared endangered, then it will get affected. So we should not log the areas which are some habitat of some endangered species, right? So we will say to avoid disturbance to the sensitive wildlife habitat, we will not log, we will not consider logging in those areas. So we will simply remove them out. Now, if these are our 4 criteria, then what is the next step? It is to select the right parameters for integration. So let us say, we'll go one by one for each steps in this. So to be profitable, ponderosa pine species to be logged. Now where do I get this information? I get it in vegetation map. So I require a vegetation map to perform this, to process this criteria. For this I require either directly the slope map. If I don't have slope, then I can get it from, I can calculate myself from digital elevation model, or I can have even spot heights or contour maps from where I can make the digital elevation model, and then I can make the slope map. So I require a slope map to process this criteria. For the third criteria, I require a map that will tell me where are these water bodies, then only I will create this buffer of 400 meters. So I require a map which can tell me where are water bodies. So I need a land classification map, basically land and water. Okay. So land water map or whatever map you call it, but you basically require locations of water bodies. Then to avoid disturbance to sensitive habitat, I require a wildlife sense. That map is already available. It is prepared by Wildlife Institute or Wildlife, the agency or organization which is taking care of the wildlife. They will have such maps. So you can straight away take those maps from the respective agencies. So for example, you could take a wildlife habitat, sensitive wildlife habitat map. So I require these maps, I have identified. So I have identified the right parameters that I require for integration. Now I will get these maps and I will input it into GIS system, either by the way of digitization, if they are in hard copy, or in scanned form. If they are already available in a GIS format, then I will simply import into my format. If I am working on shape files, I will integrate them as shape files. Otherwise, I need not do any import. But if I am working in a specific proprietary data set, then I will need to import it into that particular format. So whatever be those steps, I need to get the data into the GIS system. Once I have this data in GIS system, then I will carry out integrated modeling. So how do I do that? I am just explaining you a depiction of what will happen in computer system, and then we will talk about those functionalities and tools that are actually required to process, to do this kind of exercise. Okay, so let us say, so you see I put a dots here. This dot says that the list is may or may not be complete. It again totally depends upon how exhaustive analysis you want to make. So you could keep on adding the criterias like this. I'm just taking these 4 criterias, right? So let us say that I have performed those operations and my data is ready to be integrated. So let us say I have a ponderosa pine map which looks something like this. Okay, these are 5 patches where the this ponderosa pine species is available. This is a vegetation map. Out of that, I have taken out only the ponderosa pine. So I have already done some querying here and taken out this ponderosa pine. The next criteria I talked about was slope. So let us say I have already obtained a classified slope map. This is after performing the spatial operations, because even if I have a slope map, I will have to classify it for slopes more than 20 degrees and slopes less than or equal to 20 degrees. Okay, so let us say that we have done that as well, and these are the red ones. The red slopes are the ones that are steepy slopes. Okay, similarly, let us say I have performed the spatial and tabular operations involved in getting the sensitive habitat. Actually, sensitive habitat does not require any processing such operations, because you are simply going to remove them from your study area. So there is no processing required actually for the sensitive habitat map. Just these are the sites for sensitive habitat and we have to remove them, we have to avoid them, right? So if I carry out integrated modeling in GIS, physically how it is going to look like I am going to show you, but actually what operations have to be performed to get that we will discuss in the later part. So let us say we have, okay, then one more criteria was there about the wetlands. So we said that 400 meters of wetlands we will not log. So we will have to create a buffer of 400 meters. Let us say that we have created this buffer and it is like this. Let us say this is my buffered wetland map. So these areas have to be also removed from my study area. Now if I integrated them all together, this is how it looks like. This is a physical overlay, physical look of what it will look like, but the actual logical overlay will be something different. Okay, so this is how it is looking like. So the first layer, and then I have kept on putting the other layers on top of it. So which are the areas which will be satisfying all the criteria? It is these visual green areas which will satisfy all the conditions, because this area cannot be logged. It is affecting the water quality, this is affecting the sensitive habitat, this is affecting the steepy slopes, so the soil erosion. So the visible greens are the portions that are satisfying all the criteria from where I can finally log my trees without harming the environment based upon the criteria that I have set. So this is how it looks like, final sites. Now I can at this stage also keep on adding my criteria. So if I say that I don't want to log all the trees at one time, I will do it in a phased manner, so that by the time I go for phase 2, there are some plantations that are already grown, the younger plantations are already there, so that it does not, I do not lose that species at large. Or I could say for the transportation convenience, I will log only from certain areas which are closer to my transportation method, or maybe my path of transportation, or I could say I will not log from the smaller areas. So I will log only from the areas that are bigger patches. Whatever be my criteria, I can keep on adding, and I can try to refine my analysis. So here I show that these are the final 3 sites I have chosen based upon the adding some more criteria on area and phases, and in these now I can further decide that I can take first area, maybe one area in phase 1, another area in phase 2, and phase 3 in phased manner I could do, or whatever based upon my requirement I can refine this analysis. So the idea here is that you have an objective, you have a purpose. That purpose will tell you what is your objective, and then you make this objective more crisp by giving the criterias, and these criterias you based upon these criteria then you collect your right parameters for integration. You bring those variables and input into computer system, into the GIS system, and then try to prepare your data for analysis. Then you perform actually the integrated analysis or modeling, and then you come out with some outcome which you can further refine, and then finally you can do the reporting and output generation. So these are the steps followed in a GIS project, and I showed you with an example of logging from forest. But I have, how will you actually do it? This is only physical, visible thing, but how you will actually get in the computer system, for that we need to understand what are the functionalities. I just told you about the categories of functions that are available to do all of this. So that is what we will now discuss in the rest of my lectures on spatial analysis, so that we can come out with such kind of result. Okay, so we can come up, we can discuss, relook at this example with those operations and understood and learned, so that we can know each and step. Actually there are many ways to do the same thing, so there will be many answers to this, solving this kind of problem. You all can have your own unique ways of solving this problem, your own unique steps to solve this by using various types of operations in GIS. So we'll discuss about all those operations and functions for spatial analysis in these subsequent slides. So as I said that these are various category of operations in spatial analysis: retrieval and selection, measurement and classification, overlay operations, neighborhood and connectivity operations. So today we will see some of these, maybe up to maximum up to classification, and these we will discuss tomorrow. Maybe classification we may discuss today or tomorrow based upon the availability of time. So the first thing I want to discuss is the simplest thing that is available in your keyboards. All these arithmetic operations, these relational operations, less than, more, greater than, less than, equal to, all these not equal to, addition, subtraction, multiplication, division. These are all available in your keyboard itself. But how we can make use of them in GIS, I'll show you. Okay, so arithmetic operations, these divisions, all these 2 type of divisions, the geometric, sorry, this is geometric operations, trigonometric operations, and all of this you can perform. So like I'll give you an example of a very simple operation here. Raster 2 is equal to raster 1 multiplied by 5. This simple multiplication of raster 1 by 5, which is leading to raster 2, is an example of exaggeration. If you actually do this, this is going to exaggerate the values. So even the minute differences will be visible to you. So simply multiplication can help you, although it is just by a simple constant, it can help you visualize your data in a better way. It is something like a zooming operation, right? Then these are the relational operations. Like I just say C is assigned as not AA not equal to B. That is how it is read. This is assignment symbol, and this is not equal to here. So this is true when the cell values of A are different from that of B. If these are same, then the C will result into a false. If these are different, then C will be resulting into true. So it means that the C will be basically C will be telling where A is different from B. Now if I use this A and B as the two maps of the same area but of different times, then C is going to reveal the changes that have happened or the differences in A and B. So suppose we are talking about land use land cover map of any area, and we take A as, let us say, land use map of 2010 and B as land use map of 2020, then this is going to show us, the C is going to show us the decadal changes that have happened. It will not show what has changed from A to B, it will show both, what is different in A and B. So we can further segregate and take out the additions or subtraction that have happened in land use land cover from A to B times, but this is basically going to show you the differences. So a simple operation of not equal to can reveal so much of information. So it depends upon how you use these operators. You can bring out lot of important information out of these simple operations, right? So there are many other operations like area is less than 400,000. So if I run this query, I am going to see all the areas that are smaller than the threshold. Here the threshold is chosen 400,000, but you can have any number, any unit, you can have any symbol here of the relation out of these. So what will be the outcome looking like? In the tabular form, if you see, it will show all the areas that will be less than 400,000. So they are all selected here. The bigger ones are not selected. And you see this one is larger digit, so it is not selected. This is also larger, so it is not selected. These digits are larger, not selected, but the smaller ones which are satisfying this query are selected. And this is also visible in the map display of it, of these selected features. You do not see the larger areas like this or like this, only the smaller polygons are selected here. So this is a simple query, but it reveals a lot of information. Where are these smaller polygons? Okay. Now the other category of operations is logical operations. Some of you might have already studied these AND or NOT, which are the basic operators, and XOR, NOR and NAND, that are the derived operators. In your electronics or operations research or various other courses, you would have logic theory, you would have read these operators, but today we are going to see their use in GIS. So we can use these logical operations in GIS also for carrying out spatial analysis, for combining various layers, various conditions. So let us understand them. So whenever you perform a logical operator, there are three things that needs to be there. One is the operand, the data elements that we are going to operate upon, the operators, the relationship between these operands or the data elements, and the outcome. The outcome will be the cell values that will be either true or false. If we are talking about the Boolean theory, if we are talking about fuzzy theory, then we will have more gradual output, or it will be different, but it will still be there has to be some cell values there as well. Okay, so these three things are basics of logical operators. We'll see how they look like. So I am just telling you what is the definition of these AND or NOT and XOR. These are the most commonly used operators in GIS. So I am talking about them, but theoretically there are many more operators than this. The basic ones are three: AND or NOT. The other ones can be derived from these three basic operations. So the first one is AND operation, which says that A and B, here A and B are the data elements or the operands, AND is the operator, and the C equal to A and B, the C is the cell value of the final outcome. So A and B is true if and only if, this is important, if and only if both A and B are true. It means the outcome C will be true only when both conditions are satisfied. Even if one condition is not satisfied, the output will not be true. A or B is true if any of the inputs is true. So it is like a either or operation, or you can say this one is an intersection operation, this one is a union operation. I will also show you their set theory equivalents. So A not B is true when A is true but not B. Similarly, B not A you can say. And then finally A XOR B. XOR is nothing but the mutually exclusive OR. So it is exclusive OR, it is called. It is mutually exclusive operation, which means it says that A should be true but not B and B should be true but not A, which means difference. Again, A XOR B is similar as C is assigned as A not equal to B. Okay, so A should be true but not B, B should be true but not A. Both of them should not be true at the same time. A and B should not be false at the same time. A and B should not be true at the same time. So if that is the condition, then A XOR B will be true. So either A is true or B is true but not both. So this is a mutually exclusive. You can also derive exclusive OR by minusing the AND condition from the OR condition. It will be more clear when I show you the set theory equivalents. Let me show you that. So A and B, it will look something like this in set theory. A and B is like this. When both the conditions are satisfied, that is the intersection. A or B is like union. A XOR B is like mutually exclusive or exclusion. The AND part is minus from the union. So if you say union minus intersection, you get exclusive OR. And finally, A not B, A should be true but not B. So if I say A not B, it is like this. If I said B not A, it will be like here. When I combine A not B and B not A, then also I get A XOR B. So this is how I can derive XOR using AND, OR and NOT. So that is why we call this XOR operation as the derivative operator. Fine. So these can be used a lot in GIS for carrying out analysis. I'll show you some example of it. And then we have retrieval and selection operations. The pixel information is a very useful tool in any raster GIS package. You will find a pixel information, or even identity tool is also there. In vector also you can use it, and you will reveal lot of information with this pixel information and identity operation. Identity information window, the information window basically. Identify. Okay. Then spatial selection operations, you can do it in interactive mode or using attributes or using spatial relationships. So we'll also learn about spatial relationships in a few minutes. So I'll show you some examples of data retrieval and selection. First, let us understand what it is. It involves selective search, manipulation and output of data without requirement. Please note this, without requirement to modify the geographic location of the features involved. This is very important. When you do the retrieval, it does not modify the geographic locations of the features. Okay. Linked spatial and attribute data are retrieved. No changes are made in the location of spatial elements. No new spatial elements are created in case of retrieval and selection operations. Examples are like this. If you want to know what exists at a particular place, where are steep slopes, where is dense forest, those kind of questions are retrieval and selection operations, and all the operations that are performed using logical, arithmetic and conditional operators, these are all retrieval operations. Okay. So for example, this is data retrieval using the pixel information window. This is an example of a raster based GIS package. This particular example is from IIRS software, which is Integrated Land and Water Information System, which was developed by ITC Netherlands. Now it is part of University of Twente. It is a department of Geoinformation Science and Earth Observation in the University of Twente, Netherlands. So this window, the pixel information window, there is a map window and there is a pixel information window. So when you move your cursor from one point to another, the values here will change. Okay, so you can display all your maps here in the map window. Corresponding pixel information window will also have all the attributes associated to these maps. So this particular slide shows only for one particular pixel what are the values, what is the rock type, what is the slopes, what is the soil type, and the XY coordinates. So just by clicking here you can get all the information in the pixel information window, also in the map window, right? This is one of the tools. Then another way of doing it is, this is the map window wherein we are seeing a vector map, and instead of dragging all the layers in the map window, they are dragged in the pixel information window. You see here IIRS pixel information shown here. So here you have the geology map and all the relevant details, even about the rainfall, the DEM, the digital elevation model, the land use, geology, lithology, all of this information is present here. It is dragged to this pixel information window. So just by moving your cursor here, by looking at only one map, you can see all the relevant information which is georeferenced, that is present in the data set. Okay, so this is a very useful tool for doing a quick reconnaissance, online reconnaissance survey kind of operation you can do here. And then I'll talk about the spatial selection queries. You can do interactive selection, you can do selection by some attribute conditions using these operations which we discussed, by combining various operations, and also spatial selection using topological relationships. So I will show you these few operations of retrieval and selection one by one. So this is like interactive selection. You can select, you have a table, and in this table you can select a particular record. Accordingly, the corresponding map window will be the map, that particular element or feature in the map window will be shown as highlighted. So this is the one that is selected. Okay. Similarly, you can have selection in the map window. Its selection will be reflected in the tabular data. So I drag here and make this circle with the dragging using my cursor, and all the elements that are connected, that are selected here, they will be shown in the tabular information also. Their corresponding records, their attribute information will be shown here, right? So this is the interactive selection. Then we can also select by attribute conditions. As I showed you, area less than 400,000 is an example of selection by making SQL statements. So you can display the result both in map and the attribute table, and you can answer questions like where are those features within this much distance, or like that. So these examples are of selection by applying certain operations. I already showed you area less than 400,000. Let us also see combining the relational and the logical operations to answer these questions. So let us see them one by one. So area less than 400,000 we had already seen. Now let us also add one more condition where land use is 80. Now 80 could be some code. It could be code of wasteland or something. Suppose we are interested in finding where are those small patches of wasteland. Suppose my land use code for that in the table is 80. So I will launch this kind of query, area less than 400,000 and land use is 80. Show me all such lands. So it will show, you see, number of polygons has reduced here as compared to that table. Now there are only, let's say, 5 records selected here. So but these 5 are shown here because I cannot display the entire table, but maybe there are more polygons that are fulfilling this condition. So all those smaller polygons which satisfy both the conditions are displayed here in red color, highlighted in red color. Okay, so this is how we can combine various operations and various types, various set of criteria using the logical and the relational operations to answer some of these questions. These are very smaller queries, but please note your final query will be a bigger project. If you take, it will be having many such queries to be performed and some more operations to be performed. Okay. So we'll come back to this ponderosa pine after we have learnt all these functions, and then you can also decide and tell us what kind of queries you will perform to get those visible green portions, right? Now let us talk about spatial relationships for some time, and then we will see some examples of those, and maybe then I can close the session and I can take it up tomorrow from where I ended here. Okay, now there are several spatial relationships. Let me name this as polygon A and this as polygon B, the black boundary polygon as polygon B. So I call them as disjoint when they are not touching the boundaries. So this is disjoint relationship. So spatial relationship is nothing but the physical relationship between these features in space, and there are several possibilities. So I am discussing those possibilities here. So one of the possibility is disjoint. When A and B boundaries do not touch, they are separate, they are called as disjoint. When they touch, when they meet, this is called meet. When they exactly fit one over the other, it is called as equal relationship. When they overlap, means some part of A is falling in B and B is falling in A. This is an overlap situation, so we call it as overlap relationship. When the condition is like that, B is covered by A, so it is covered by, here B covers A, or A is covered by B. So these are similar, the relationship is same, but it is reversed if you talk from perspective of A or B. And then you have B is inside A, or A covers B. So here A covers B, or B is inside A. Here B contains A, or A is inside B. So contains and inside are also the same relationship. It depends upon from whose perspective we are talking, from the perspective of A or B. Same is for covers and covered by. These are not interchangeable. Or actually they are interchangeable. They are like A and B are disjoint. A is disjoint from B, B is disjoint from A. A meets B, B meets A. A is equal to B, B is equal to A. A overlaps B, B overlaps A. But here we cannot interchange. We cannot say A is covered by B, B is covered by A, right? We will say A is covered by B, B contains A, like that. So similarly, A is inside, or B is inside A contains B. Now please notice the difference between contains and covers. Here B contains A, here B covers A. So when it just covers, it touches and covers, then it is covers. If it is completely inside B, A is completely inside B, then it is called as B contains A, right? So that difference you can note down. Now how we can make use of this, having talked about these spatial relationships, how we can make use of these spatial relationships. So I'll show you some of the examples. Like here, these are some cities in US. Now I want to select all the cities in a specific state. Let us say the state of Georgia. So to get this answer, I need to perform two steps, two queries actually. One is I need to select the state of Georgia, and then so that I will do using the attribute query, because I know that this name of a state is stored in my attribute table, not in my spatial table or spatial information. The map does not have the name of the state. The name of the state is in the attribute table. So I will perform one attribute query to select the state of Georgia. So the moment I do this attribute query to select the state of Georgia, this state is highlighted in yellow color. Now I will perform one spatial query, because I'm interested in all those cities that are inside this particular polygon, which is the state of Georgia. So I will say select all the point features, which are the cities that are inside. I will use the inside relationship. Inside with what data I will use it? With the state of Georgia. So select all the cities that are inside the state of Georgia. So to perform this query, to get this answer, I need to make two queries, one attribute query and one spatial query. I hope that is clear. So select all the cities that are located in the state of Georgia using inside relationship. Now if I have to find out all the roads or let's say highways that cross the state of Georgia. For that I would need overlap relationship, right? So I need to perform one attribute query and one spatial query. So this is an example of use of overlap relationship. And then similarly I can find out all the neighbors of a particular state with the help of meet relationship. So likewise you can perform various queries using these spatial relationships. They are very useful and I hope you understand how they are used in GIS. We will take up some more further analysis maybe in tomorrow's session. So one more I will show you, the relationship of distance, which I did not talk about. This is the 9th relationship, you can say. The other 8 I already discussed. So let us say I am selecting here one city, let's say Atlanta city or something I am selecting here in the state of Georgia. I want to see all the cities that are within, let us say 100 kilometers or 100 miles from the city of Atlanta. Then I will make a distance relationship. I will calculate the distances of all the cities from this particular point. So a kind of virtual buffer we are actually creating here. Within 100 miles, whatever cities are there from this particular city, those will be resulted. So just one spatial query will do here. So distance relationship is used here to find out all the cities that are within 100 miles from the city of Atlanta. Right? So I would like to end the session here for today, and classification we can take tomorrow because it is already 79. We can have an interactive session. If you have certain queries, I can try to answer them now, and we'll take up the rest of the functions tomorrow. Okay, thank you.